All right, thank you for having me here. I'm ambitiously and maybe slightly modestly going to ask the question, how can we trust machine learning? And as Anthony just said, I recently moved from the University of Washington, and I had to submit a bunch of information to Stanford during the process, including my teaching evaluations from my machine learning class. But I strategically hid this one. Professor Guestrin, I'm very disappointed in your class. I thought machine learning was going to be magic, but it's just math. This quote is from some years ago, where there was a significant myth around machine learning, that it was just math. Where you started from data, you put in some machine learning math, and you ended up with profit, which at the time meant showing that my curve was better than your curve, and then publishing a paper at a top conference. But there must be some magic in machine learning, because we've seen it had tremendous impact in the real world. Solving open problems that have been around for a long time, like winning at Go, driving cars around by themselves, or making predictions and screening about your health in all sorts of new ways. And what I think about as the magic in machine learning is really what happens in the space between the math. Really, the question is, how do you define the problem you're trying to solve? What data do you collect? How do you define and train your models? How do you integrate it into the bigger system? How do you deploy these? All questions have been discussed today. And at the core of these, how do you evaluate these models? So in this very complex pipeline, the machine learning math has an important role in it. But this pipeline is filled with complex human decisions. And as machine learning is making more and more automated decisions for us, and the systems are getting more and more complex, we might ask ourselves the question, how can we trust machine learning in the first place? And I'll approach this question with a simpler question, perhaps, because less is more. How can we possibly trust? This question has been explored in many ways. In medicine, there's this seminal paper from 2004, where they looked at issues of trust in your provider and saw that people that trusted their provider had increased adherence to their treatment, increased continuity of that provider, and better outcomes, while lack of trust led to lower rates of care seeking, of preventive services, and seeking surgical treatment. And so thinking carefully about how you might trust a provider has a significant impact on your medical outcomes. And they were able to study the notions of trust and found three areas that were important in terms of trusting a provider. One is technical competency. Do we believe this person knows what they're doing? The second one is interpersonal competency. Does this person communicate well with me and helps me understand what's going on? And thirdly, agency or loyalty. Does this person have my interests in mind when they're making decisions? This is really interesting and I think really relevant to what we're doing here today. And so with that in mind, we might ask the questions of what are the core trust principles for machine learning? Now, when I think about this, I think about trust for whom? Who are we trusting and how we're thinking about this? Can I trust what I am building is a question I ask myself a lot. Can you trust the thing I built and I'm making you use? Or as a community, can we trust the things that we're building and that we're doing them for the right reasons? These are all hard questions. Today, I will humbly just look at the first one. Can I trust what I'm building? And I'm going to propose three notions that are going to be important in what we build. Clarity, competence, and alignment. Let's start with clarity. Simple word. Clarity is really the quality of being easy to understand. And many of the models that we're trying to build and the systems we deployed are not easy to understand. Now, there are many ways to address clarity. We saw James do some really good work, present some really good work just before this. In my group, we thought about clarity in the context of interpretability. Interpretability is about giving a human a mental model of how the machine works. A human, a mental model of what the machine learning model does. You can do this in many ways. You can pick a very simple model like a shallow decision tree. We know exactly what it's doing. Unfortunately, these models don't tend to perform very well in practice. You can pick more complex models, like maybe a very big decision tree, that might perform better, harder to understand, or state-of-the-art deep learning models that maybe achieve superhuman performance, but are incredibly complex to understand. And to me, interpretability is not about picking simple models necessarily, but it is about solving really complex real-world problems, but helping us understand when they're working and when they're not working. And we started this effort several years ago with an approach that we call model agnostic interpretation. So we think about the machine learning model as a black box and being able to explain any black box model. With this, we can explain state-of-the-art models. We can explain models that exist today and models that come up in the future. And you can compare two models that have nothing to do with each other. Although the space of decisions of a model may be very complex, our first endeavor in this was a system called LIME, which started from a very simple assumption. Although the space is very complex, if you zoom in around each prediction and you zoom in further, the space around the prediction might be simple. Maybe it is even linearly approximable. So what LIME does is try to find local linear approximations for every prediction the model makes. So let me give you a quick example of that. Let's take this image here, and we send it to an image classifier, neural network, and we ask what parts of the input were important to make certain predictions with respect to this image. Well, the model says this is an electric guitar with probability 32% when it's looking at this part of the image. It says it's an acoustic guitar with probability 24% when it's looking at this part of the image, and a Labrador with probability 21% when it's looking at this region of the image. In other words, we're able to decouple what parts of the input were important for particular predictions it was making. As another example, there's a famous data set called the Training News Groups data set, which is a text data with various categories. And it was such a simple data set that any simple machine learning approach does really well on this data. So I've always used it in class. For example, simple classifiers to separate text between atheism groups and Christianity groups gets 94% accuracy. What my student Marco did as part of this project was go and inspect why these predictions were so accurate. And what he noticed is the features that were important for making these predictions were things like the email address of the sender. So for example, john@atheismsareus.com always posts in the atheism blog group. When you remove that kind of information, when you look at recent data, the accuracy falls down to 57%. So really the model was performing well. It was used across a large number of machine learning papers, but it was used in a way that did not capture the characteristics of the real world. Marco then did a mechanical Turk experiment where he trained the model on the old data set and evaluated on the fresh one and got 57% accuracy. Or then he trained on the new clean data that he cleaned himself with hard work and tested on the new data set, and the accuracy improved significantly. And then he took mechanical Turkers with no machine learning expertise and showed them the explanations of what was happening and asked them, cross out words and terms that you don't think should be part of the prediction. And with just 3 rounds of mechanical Turk experiments, he was able to obtain better accuracy than he did himself cleaning the data. So I fired him. Joke. It was great. So to me, interpretability in machine learning is really about giving us a great mental model of how the machine works. And there's many ways of doing this, and there's been a lot of work since at trying to give better and better understanding of what's happening inside the scenes, behind the scenes. So for example, from our group, from Marco, Lime was trying to do a local explanation. Other types of explanations might ask are, for example, where are regions of the space where the predictions are stable? We call this anchors. So if you were to perturb the input around those regions, the prediction will not change. If you do that, you discover some really interesting characteristics. So for example, take a task called visual question answering. It's an amazing task. Give this image as an input, and you ask a question like, what is the mustache made of? And the model says, banana. That's pretty cool. How many bananas are there in the picture? And the model says 2. It's pretty awesome. But if you look at anchors, so if you look at what's stable in this input, for the first question, it's the word what. And for the second question, is the word many. In other words, any questions with the word what have the answer banana. So for example, what is the ground made of? Banana. What is the hair made of? Banana. What is the head of the United States? Well, you get that. And the word many was the anchor for the second question. So for example, how many people in the picture? 2. How many is too many? Obviously 2. So by really trying to understand why a prediction is made, we can help understand whether the model is addressing things for the right reasons. And clarity is important also for human decision-making. So if the model is being used for making important medical decisions, for example, like James was talking about, it's important to understand what is the basis of this prediction. And there's been some interesting follow-up work, not from my group, where they've used these notions of explanation to detect hypoxia, so loss of oxygen, during surgery. And by combining predictions with explanations, they were able to get better outcomes, which is pretty impressive. So to me, clarity is really important, really understanding what's going on behind the scenes. But competence is also a fundamental property of these models. So competence is the quality of having sufficient knowledge, judgment, skill, or strength as for a particular duty or a particular respect. And this is a hard one. That means that you're doing enough, you know enough to solve the task at hand. And we don't talk about that too much in machine learning, at least in machine learning papers, but really it's about having sufficient skill for solving a problem. And when we think about this, we think about competence in terms of evaluating models. So in 2008, it might have been competence or sufficiency was about my curve being better than your curve. But even the notion of a fixed test data set that is given is a naive notion in practice. And so when we think about building and evaluating these models, we need to take a different approach or a different perspective. And I think a lot about a software engineering perspective in this. When we build good software and you do good software testing, you think about failure analysis. When is this working, this not working? And you think about systematic testing. Can I try to break it? Can I explore the boundaries of the system? And we do need to do better in this space in machine learning. I'll give a couple of examples of work in our group. The first I think about as adversarial bug discovery. So you have a particular input X in a particular classifier. Can we think about perturbing this input in a way that will change the prediction? And this work has been going on for a little while. So for example, there's really important work where they show that if you take an input like this one, and you add a small amount of strategic noise to it that is imperceptible to a human, then the prediction will change from a panda to gibbon. The problem here is that the perturbation is imperceptible to a human. So not so relevant for many tasks, maybe relevant for security, but maybe not relevant for natural human input. And it's unlikely to make a difference in the real world except for adversarial attacks. The type of problem we want to find are like this ones. If I give you this input and I ask what type of road sign is shown, this amazing model says a stop sign. Or if I give you this paragraph and I ask how long is the Rhine, this amazing model will say 1,230 kilometers. But with small perturbations like which type of road sign is shown, now it's do not enter. Or if I change the question, the second one, from how long is the Rhine to how long is the Rhine, with 2 question marks, now it's 1,050,000 long. So what we can discover is when we think about a semantically equivalent adversarial examples. So the idea here is to perturb the input in the ways that make sense. So in text, it will be paraphrasings, but they make the model confuse or change its prediction. So for a particular input, like what color is the tray, pink, paraphrasings here might be what color is the tray with a British accent, or which color is the tray. And each one of these has changed the output of the model. This tells us a lot about the space of when the model is working and what's not working, and what we might be able to do about it. So in the example that I said, going from what to which reduces the overall accuracy by 4%. Adding an extra question mark to questions reduces the overall accuracy by 3%. Automatically discovering decisions and improving the models can add robustness and make a difference. So for example, a simple approach might take on some standard tasks is to do some data augmentation based on these bugs that you discover, and that can significantly improve the robustness of the model, just through simple data augmentation. So machine learning models are prone to such bugs, and it's important for us to focus on semantically meaningful ways to address them. But really, how do we know that we've done enough of this? Or how do we think systematically about testing these models and making them better? And this is where I think we can learn from software and think about testing models like we test software. And last year, Marco and Tongshuang, another student, worked on a system we call Checklist for behavioral testing of NLP models. Let me use a simple running example with sentiment analysis. Let's say you have an input, easily the best airline in Seattle. Oh, sorry, I should say, easily the best airline in San Francisco. I give it to this model, sentiment classifier, and I want an output. Is this a positive sentence, a neutral sentence, or a negative sentence? A core principle of testing is to start by testing small units. In this case, we're going to think about testing small linguistic capabilities.